In this discussion, so we are going to discuss about how to derive the expression for attenuation constant, which is alpha, and the phase constant, that is beta, for a uniform plane wave in a good conductor. Just imagine that the electromagnetic wave is propagating in a good conductor. So, what would be the value of alpha and beta? So we have studied earlier the propagation constant, the gamma, which is a complex number. So gamma is the phase constant alpha plus j beta. Because we know that electromagnetic wave that is subjected to the amplitude change and phase change. If you look at this figure, we can see that the amplitude diminishes, and also there is a phase difference. That phase difference, which means uh, the this the distance between two adjacent crust or trough, which is being changing over the time, over the distance it is traveled. So is a direction through which it is propagating. Now this alpha is the attenuation constant, and beta is the phase constant. Now we have earlier derived the expression of gamma. It is can be written as it's a square root of j omega mu, and within the bracket sigma, the conductivity of the medium, and j omega epsilon, the square root. And here, what is the value of alpha and beta uh, of a good conductor? So good conductor, we know that it is sigma by omega epsilon is much greater than 1. And let us take out this j omega epsilon outside. So this become j omega mu times j omega epsilon. So inside the bracket become j omega epsilon plus 1. So for a good conductor, sigma by omega epsilon is much greater than 1. So we can remove this term, this 1, because that term is much greater than 1. So the sigma by j omega epsilon plus 1 is sigma by j omega epsilon plus 1 is approximately equal to sigma by j omega epsilon. Now here we can see that on the numerator side and denominator side, the common terms are there, so it get cancelled. So finally we can write it now as j omega mu sigma. Now here we can see that there is an imaginary term, so we can write it down as omega mu sigma, and also that is multiplied with square root of j. So what is the square root of j? So for that we need to use the Euler's principles. Euler's principle, we know that e power I theta is cos theta plus j sine theta. If theta equal to pi by 2, then e power, if theta equal to pi by 2, this above expression become e power j. Let us use j instead of I. E power j pi by 2 is cos pi by 2 plus j sine pi by 2. So cos pi by 2 is 0 and sine pi by 2 is 1. So this become j. So e power j pi by 2 is equal to j. Now let us take the square root on both sides. E power j pi by 2 odd power 1 by 2 is equal to j power 1 by 2. So what is this? E power j pi by 4 is equal to square root of j. That means square root of j is cos pi by 4 plus j sine pi by 4. So cos pi by 4 is 1 by root 2, 1 by root 2 plus j 1 by root 2. We can take out 1 by root 2 outside. So 1 by root 2, it's a common 10. So it will become 1 plus j. So this is the square root of j. Now let's just substitute the square root of j here. And so the gamma become square root of omega mu sigma multiplied with the square root of j 1 by root 2 1 plus j. So let us multiply these terms inside the bracket. So it become omega mu sigma plus j times omega mu sigma 2. So compare this to alpha plus beta. So alpha plus j beta. So this term is alpha and this term is beta. So alpha become omega. So omega is 2 pi f mu sigma by 2. 2 get cancelled, and similarly beta is equal to omega. So omega is 2 pi f mu sigma by 2. 2 get cancelled. So alpha is pi f mu sigma square root of pi f mu sigma, and beta is square root of pi f mu sigma. So the unit of alpha is a Napier per meter. Napier is a logarithmic unit, and beta is a radian per meter. Radian is connected with the degree. So this is the amplitude constant and phase constant of a good conductor. So all the derivations start with an assumption that for a good conductor, sigma by omega epsilon is much greater than 1.